Hello everyone, welcome back. Okay, so this time we're going to talk about material selection and how we have to look at the physical properties of materials to understand what we need to choose or how we need to process them to meet our desired result. So first off, we have usually we have sort of a procedure for material selection problems. Like, okay, do I use metal or do I use wood? Let's find out. So first off, for a specific application, we have to determine the required properties. Like mechanical, how strong does it have to be? How much can it bend or stretch before it should be able to break? Electrical, should it be conductive? Should it not be conductive? Thermal, should it be able to take high heat without yielding? Magnetic, should it be magnetic? Optical, should it be clear? Should it allow light to go through? Should it filter some sort of light? Deteriorative, how does it break? Does it just go? Does it slowly stretch? Does it give very slowly? There's lots of different ways you can break. You don't want it to explode, unless it's a bomb, I guess. But in most cases, don't let it explode. Okay, now for this list of properties, you identify candidate materials. For example, if you want something very strong, plastic's probably not going to work for you. If you need something that has a very high thermal conductivity, well, that's not going to be plastic, not going to be ceramics. But metals, they're very highly conductive and they're strong. So then you choose the best candidate material, and then you have to determine, well, how am I going to process this? I want to make it as strong as possible. I don't mind if it's brittle. Well, I have to process it in a certain way. Or maybe I want it to be very flexible. I want to be able to bend. I don't mind if I lose some strength for that. You process it differently. And you have to make sure you can take into account, well, one, how to get the required set of properties. Two, will it be able to produce the component having the desired shape and size? And different techniques you're thinking of here. Welding would be one. You have to weld it together. That does change the mechanical properties. Mechanical forming, it's like bending it or putting it in sheets. Casting it, you melt it down and then you pour it into a mold. Heat treating it, you get it into the shape you want, and then you process it by heating it up and then cooling it slowly or very, very quickly. Just depends on how you want to do it. Okay, what kind of material property types are there? Well, we're going to focus on a few right now. We're going to go for mechanical, electrical, and thermal right now. So those we're going to look at right now. Now, mechanical properties, mostly we're talking about the hardness or the strength of a particular material. For example, what you should know is that as you increase the carbon content of steel, it increases the hardness up to a point. Eventually, you just have pencil lead if it's 100% carbon, which is not a good thing. Okay, and also notice that this is not 100% over here. This is 1 weight percent, so this is 1% carbon by weight. Electrical properties. Well, like copper. Copper is used for electrical wire. You want it to be electrically conductive, which is inversely related to resistivity. The more resistant it is, the more energy you waste as heat as electricity goes through it. So depending on how you add in more nickel or less nickel, or how you deform it, it will actually change its resistivity at different temperatures. It's going to heat up most likely, so you're going to see the resistivity actually rises as it gets hotter and hotter. Not necessarily a good thing. Now, this is 0 degrees Celsius. This is negative 200. So if you want low resistivity, keep it super cold, which is why you see those computers, when they really want to run fast, they pour like liquid nitrogen on them. Kind of crazy. Now, one other question you might be wondering is, well, why does deformation increase your resistivity? It's because electrons need to flow through, and if there's some nice clear pathways, like you haven't bent it at all, it's just all these atoms right after each other, it's easy to flow. But as soon as you start bending that guy back and forth, those atoms pop out of the way, and it's just like having a bunch of cars in the middle of the street. You can't go anywhere. Traffic jam. You're having to flow around them. So less brakes, less balls in the way, easier for electrons to flow, so less resistivity. Okay, finally, thermal properties. Well, thermal conductivity is a measure of a material's ability to conduct heat. Okay, can it conduct heat from one side to the other? Metal's really good at that. It's hot on one end, it's hot on the other. Wood, not that good at it. Ceramics, not that good at it. I mean, the space shuttle, it is covered in ceramic for a reason. It keeps it safe. It has these nice layer of shielding, and so astronauts inside don't turn into pancakes. That's why we had that horrible issue when there was a piece of foam that hit, knocked off the shielding, and it caused it to explode. So, if we're looking at things like, okay, let's see right here. This is going to be copper, zinc, and copper. So the more zinc we have, the less thermal conductivity we have. That's probably because of the different defects that causes. It causes little stresses and strains, which make it harder for the heat to be transferred. Okay, interesting little details here. Highly porous materials are poor conductors of heat. Now this is based on microscopic structures. You can't see this. Notice the micro. That's a little look like kind of like an M or a U with a mullet. That stands for micro. And this microscopic structure has all this empty space. So much empty space. And as a note, air is a terrible conductor of heat. You're like, but what? It's not terrible, like my oven. Well, what's happening in your oven is that the air is eventually heating up just because it can't go anywhere. You have trapped it in there. But what's happens here is that air can't move, it can't convect, it can't leave. It's trapped in all these little porous tubes. And because of that, the heat has a really hard time getting through it. That's why the materials used for the space shuttle have all of those voids in it, all these little cavities inside of it to keep it safe. The air is trapped, it can't move. The heat's having to move through the air, which takes a long, long time. And if it's trying to move along all these little pathways, look at this. It takes forever to find its way to the other side. It's not that it's a maze, it's just it's a very long path link to get to the other side. You might have seen, and I'm going to stop after this, there are sometimes like fire pokers, and at the end of it, what they'll have is a spiral of metal that you hold on to. That's the handle. There's a poker on this side, to poke things. And there's a spiral of metal. The reason it does that is because it makes a very long path link. This can be very hot, but it has to go all the way through this long spiral to get to your hand. And by the time it's done that, it has lost a lot of the energy. The heat has radiated outward. And so that protects you. Similar here, long path link, it radiates outward. The air is not really doing much to help it. It gets stuck. As a note, right now, if you haven't done it before, go and look at aerogels. They're amazing, and they're using these cavities that are filled with air to help be very, very poor thermal conductors. Okay, so that's the end of the lecture for today. I hope you enjoyed learning about the physical properties. Next time we're going to jump into a few more properties of materials that we have to think about when we're building different products. So, I hope this helped you, and I'll see you all next time. Bye-bye.